Okay, let's operate.
Operate. Operate. Where's the dog?
It's Operation the Wacky Doctor's game where you're the wacky doctor. Batteries not included.
I flew it. My turn.
Take out a spare ribs for $100.
It takes a steady hand because if you touch the side...
Here goes his funny bone. Don't get nervous. I did it. That's $200.
Operation, a game from Milton Bradley.
Alright, welcome to section 4.3 where we're going to talk about operations with functions. Okay, this entire unit we've been talking about functions, either graphically, how we can transform them and flip them and stretch them, maybe even identifying them as even or odd, but this time we're going to talk about operations with functions, how we can add, subtract, multiply, and divide functions together. I don't know if you guys have ever played the game Operations. Okay, I absolutely hated this game when I was a kid. I was completely terrible at it. Okay, my brother always kicked my butt. But this was what the old style of game looked like, which is what we had, because I believe it was my mom's before my brother and I had it. They've come out with better versions since then, but I absolutely hated this game. His red nose would always buzz when I would hit those sides or those metal sides. Absolutely hated it. But in terms of operations with functions, what we're going to do today is a little example here. We're going to add functions together, meaning if we were to take the f function and add it to the g function, on the left-hand side we would get this little expression, but on the right-hand side we can actually combine some like terms since we're adding them together. So a 3x and a 5x would give us an 8x, but a 2 and a negative 4 would give us a negative 2. So we're going to talk about operations with functions, how we can add functions together, maybe even subtract them, multiply them, or even divide them. So let's get on with operations. So the first type of function operation we're going to talk about is what's called the composition of functions. And we're going to go over this one first because it's usually the more difficult ones for students to understand. I know you guys already know how to add, subtract, multiply, and divide things together, but sometimes it can be tricky for us to visualize or wrap our minds around these composition functions. So this funny looking thing right here, okay, it does not mean fog. This is not an O. This little symbol right here actually means the word of. So this is saying f of g, okay, literally like this. But in terms of a function notation, if we take f of g, okay, normally we have f of x. That's how, well, what we're used to is f of x. But if we take f of g, that means that we're actually putting the g function inside of the f function. Just like how we would put a number in for x, this time we're putting an entire equation in for x. So we're putting the g function inside of the f function. And you can kind of see that here, how f is on the outside and g is on the inside. We're going to put the g function inside of the f function. But we can go the other way around. Maybe we want to say g of f. In this case, we would put the f function inside of the g function. So looking at a few examples here, we're going to let our f function be x squared minus 1, and then our g function be the square root of x. So if we take a look at this composition function notation, notice how on the inside we have g of 2, and we want to put this value, whatever it is, inside of the f function. So let's just first find g of 2, because that might help us out. Let's find g of 2. So we're going to go to our g equation, which is the square root of x, and we're going to put in the value of 2 for the x, which would be the square root of 2. So now that we found what g of 2 actually is, it's the square root of 2, we want to put this value into the f equation. So we're actually now going to find f of the square root of 2. So our f function was x squared minus 1. If we put in the square root of 2 for x, we're going to have the square root of 2 squared, which the square root and the squared cancel each other out, so we're just left with 2 minus 1, which is 1. Alright, so see how we're composing functions together. We're putting one function inside of another. So we're actually evaluating both of these, but at different specific values. We had to define g of 2, so we put 2 in for the g function, but then whatever that answer was, we put that into the f function. So in the end, our overall answer would be a positive 1. Now let's try the next one. A little different notation, but it still means the same thing. This is g of f. So we're going to put f of negative 4, whatever that is, into the g equation. So let's find f of -4 first. In our f equation, if we put -4 in for x and solve, -4 squared is 16, minus 1 gives us 15. So now that we know what f of -4 is, we want to put this value into g. So let's find g of 15. If we put 15 in for x, all we're going to have is the square root of 15. Now we can't break that down. We cannot reduce or simplify that radical, so we'll just leave it like that. So our final answer in this case, after we compose our functions, would be the square root of 15. Now in this case, notice how we don't have an actual value of x. So this is just specifically talking about the functions themselves. So we want to put the g function inside of the f function. So let's just first of all start with f. Okay, so this is our f function, and inside of it, inside of this x value right here, we want to put in g. Okay, we're going to put g into our f equation. So in for this x, I want to put the entire g function, which in this case is just the square root of x. So we're going to have the square root of x in for the x, but this is squared, and we have a minus 1. Now the square root and squared cancel each other out, so we're just left with x and then a minus 1. Alright, so there we go for that one. So if there's no number there, like this -4 or 2, we're just talking about the functions themselves. But if we do have numbers, we can plug those x values in and solve for our composition function. Now here's the thing, we're going to talk about the domain for this specific new equation, because we started with this f in this g function, but now that we compose them, we have this new function. And what's crazy about this is that when you look at your new function, we're probably thinking that the domain would be all real numbers, because notice how there's no square root, there's no fraction or anything that we got to worry about. We would probably think that this is all real numbers, but it's not. Okay, the fact that this equation came from these previous ones is a really important idea. So if we take a look at the domain from our first equation, okay, there's no square root, there's no fraction, so the domain here would be all real numbers, but in this case, since we do have a square root, the domain would be x values greater than or equal to 0. So this is what's crazy. So since this came from these two equations, we got to bring these two domains together. So if we think about it, from this piece we can have all real numbers, but from this piece we can only have numbers greater than or equal to 0. So we got to take the more restrictive domain, which would be this one, because it's telling us what specific numbers we cannot use. So even though our overall answer looks like it should be all real numbers, it is actually x values greater than or equal to 0, because this is the most restrictive domain. Alright, so you can kind of think about it this way. Let's say you're going to a picnic or something, and you have one friend that's allergic to peanuts, okay, so they can't have peanuts. Maybe that's like the domain from the first part, okay, you can't have peanuts. But then you have a friend also coming to your picnic or party that's lactose intolerant, so you can't have any milk or anything or cheese. So that would be the domain from your second one. If both friends are coming to your overall party, you want to make sure you don't have peanuts or milk or cheese at all, so that no one kind of gets sick. So your overall domain or your overall party should not have any peanuts or I guess cows, I almost said, but milk or cheese in this case. So you kind of got to bring both previous domains together to help you find your overall domain. Okay, we're taking that least restrictive domain. Now in terms of a graph, if you want to go ahead and check it out, oops, I didn't mean to do that. I went in and actually typed in our composition function. So this piece right here, when I put the square root of x into our f of x equation, this is what we had. Notice how if you graph it, okay, you get this line, which is essentially this piece here, because we have a b value of -1 and a slope of up 1 over 1. So this is our overall function, our overall line, but notice how it's not all real numbers. We don't have this other piece over here. So your calculator is bringing in that most restrictive domain of x values greater than or equal to 0. Our x's, our graph is only showing up for these positive numbers, and that's because it's being restricted by this domain from our g of x equation. So overall domain has to be a combination of both of your previous domains. Alright, so let's try a few more of these. We want to find f of g of 2. So let's find g of 2 first, and then we'll plug our answer in for the f equation. So g of 2, if I take a look at my g function, I have the square root of x minus 2. So if I put in 2, we're going to have 2 minus 2, which is the square root of 0, or just 0. So now that I know what g of 2 is, let's take this answer, that 0 answer, and we're going to put it in for f. So we take a look at f, we're going to have 3 over 0 squared is just 0 minus 5, which would be negative 3/5. Alright, so there's our first one. Now the next one, notice how we don't have a number in here. We're specifically talking about x's, so we're specifically talking about our functions themselves. We're going to put the g equation into the f. So we're going to put this entire equation into our f equation for that value of x. So we're going to have 3 over the square root of x minus 2 squared, and then a minus 5. But the square root and the squared cancel each other out, so we actually have x minus 2 minus 5, okay, just the inside is left, which is going to give us 3 over x minus 7. Alright, so since we're specifically talking about equations, it might be worthwhile to maybe find the domain in this case. So what's the domain of our new equation? Well, since it came from these previous ones, we got to bring both of these previous domains into play. So if we look at our first one, since we have a fraction, the denominator cannot be 0. So if we solve for x, we would add 5 over and then take the square root. So x cannot equal that plus or minus square root of 5 in this case. Over here, since we have a square root, x minus 2 has to be greater than or equal to 0. So x is greater than or equal to 2. So our domain, we can have x values greater than or equal to 2, but we specifically cannot have a positive or a negative square root of 5. So here's our domain for our new function. Alright, so moving on to the next one, we want to find g of 0 and then plug that in for our f value. So g of 0, if we plug that in, we're going to get the square root of 0 minus 2, which is the square root of negative 2, but this is not a real number, okay? It's actually going to be imaginary. So this is not real, meaning that we can't really go any further. So since we're not getting an answer for g, that means we're not going to get an answer for f. So we could say that our answer in this case does not exist because we cannot simplify it any further. Notice how though 0, okay, if that's what we're inputting into this composed function, was not a part of our original domain. Okay, we said that x values had to be greater than or equal to 2, and 0 is definitely not greater than or equal to 2. So since 0 is not a part of our domain, that means it is not going to work, and we can clearly see that in this case. Alright, so now that we know composition functions are functions that we kind of put inside of each other, we can now talk about decomposing functions where we try to figure out what was the function we put on the inside and what was the function that was originally on the outside. So we're going to say that h of x in this case was some type of composed function where we put g on the inside and this f was considered our outside function. So take a look at our first example here. Notice how x cubed plus 1 is on the inside of this square root symbol. So since it's on the inside, that means that it was originally our g function because that's what we put on the inside of f. But if we originally put this into another equation, notice how the square root symbol is on the outside. So we would have had an outside f function of the square root of x. So all of this stuff, all of this x cubed plus 1 was put inside of this x value that was in the f of x, and we got this h of x composed function. So the inside quantity was that x cubed plus 1, and since we were left with a square root, that means we would have a square root of x as our outside function. Now over here we can kind of think about it the same way. In this case, when we're dealing with fractions, the denominator is considered the inside section. So we can say since x squared plus 1 was the inside, I guess, section, that was our g of x, because that was our inside portion. And since that's where we inputted this g of x equation into the denominator, our outside function would be 1 over x. Okay, that rational parent function that we talked about from Unit 2. So if we tried to compose it again, if we tried to put g inside of f, notice how we would put this quantity into this x position, and we would have exactly what we started with in this h of x portion. So when you're trying to decompose functions, we want to try to figure out what is the inside stuff, okay, try to think about inside groupings or inside parentheses, and then whatever's left over is considered that outside function. Alright, so now that we finally compose functions together, we can move on to these operations with functions, where we can either add, subtract, multiply, or divide two functions together. Now, in this little table here, I'd like you to fill it in. These are all of the different ways you might see these operations written. Now, I know they're very similar. Notice how the addition always involves some type of addition, same with subtraction, multiply, and divide. But these are different notations, different ways you might see these written, depending on what book you use, what professor or teacher you have. They all have their different little quirks or ways that they write things. I know that when I was in high school, we normally used these notations when we added, subtract, multiplied, and divide, but the moment I got to college, I started to see these other two over here in these two columns. So depending on what level you are, or your book, or your teacher, you might see these in a different way, written differently, but they all essentially mean the same thing. So let's just take a look at some examples here. I'm pretty sure this is going to be easy for us to do. Let's take the f function and add it to the g function. So if we write down our f function was 2x squared minus 1, and we're going to add it to the g function, which is 3 minus 5x. So if we take our f function and add our g function, let's combine some like terms. We'll have 2x squared minus 5x, and then our combined terms would give us a plus 2. So pretty simple, not too bad. But the tricky part might come into play when we need to find this domain. And very similar to composition of functions, notice how we're taking two previous functions and combining them together. So we need to take into account the two previous functions' domains. So if we look at our first function, there's no fraction, there's no square root, so the domain is all real numbers here. Same thing going on in our second one, no fraction, no square root, so the domain is all real numbers. So if there's no restrictions here and no restrictions here, that means we are not going to have any restrictions when we combine them together specifically by adding. So our domain, since there's no restrictions, would be all real numbers. Now in this case, let's try multiplying. So we're going to take our f function, 2x squared minus 1, and multiply it by our g function, 3 minus 5x. Maybe we can do some FOIL or distribution. We would get 6x squared minus 10x minus 3 plus 5x. And then combining like terms, we get 6x. Actually, maybe we'll put these in order here. Oh, I think I did a little mixy. That should be a 10x cubed. Sorry. 10x cubed, because we have 2 times that negative 5 is negative 10, and then x squared times x is x cubed. So this would actually come first. Negative 10x cubed plus 6x squared plus 5x minus 3. We'll put all of our exponents in order. Now again, since we're talking about the domain of our new equation, we got to take the previous ones into account. They were both all real numbers, so no restrictions means that our new equation doesn't have any restrictions either. Alright, so this one looks a little bit different than the two previous ones, but notice how it involves subtraction. So we're going to take the f equation and subtract the g equation. So our f equation was 2x squared minus 1, but this is where we got to be tricky because we're subtracting the entire g equation. So we need to subtract all of 3 minus 5x. So when this happens, I highly recommend putting it into parentheses because notice how we're going to have to distribute in that negative. So once we do that, it's actually going to become minus 3 and then a positive 5x. If we subtract this entire piece, I'm subtracting 3, but I'm also subtracting a negative 5x where that positive is coming into play. So combining some like terms, we have 2x squared plus 5x minus 4. Combination of our two previous equations, their domains were all real numbers, so this is all real numbers as well. Now in terms of a fraction, let's take our f equation, 2x squared minus 1, and divide it by our g equation, 3 minus 5x. Now we can't really cancel out or simplify anything, so that's as far as we can go. But this is where we got to be careful because we're talking about a domain now of a fraction. So even though our two previous answers were all real numbers, notice how we're gaining a restriction from our new equation since it's a fraction. So we don't have to worry about anything from our previous equations, but we do have to worry about something from our new one. So if our denominator cannot equal 0, and we try to solve for x, we can subtract that 3 over and divide by a negative 5, which is going to give us a 3/5. So we can be all real numbers based on our two previous domains, but now that we have a fraction, we got to consider that, and x would not be able to equal 3/5. Alright, so let's actually take a look at one that's involving a number. Okay, all the other ones we did over here, they just had an x in them, or specifically this one, it had an x written. If we take a look at one that has a number, this is telling us to add the two equations together when x is specifically 2. So let's find f of 2 first. Okay, since we're trying to add these two together, let's find f of 2. If we put 2 in for our square root, it's just the square root of 2. But now, if we find g of 2, 5 minus 2 would give us 3, so we'd have a square root of 3. But this notation is telling us to add our answers together. So if we take our f answer plus our g answer, we're going to have the square root of 2 plus the square root of 3. Alright, and that's all we can do. This is, okay, a little FYI here, this is not the square root of 5. You cannot add a square root of 2 and a square root of 3. These are considered not like terms because their inside numbers are not the same. So this is not on any planet or any universe the square root of 5. You got to keep these separate. We're not really talking about a new function here, so let's cross out domain. Didn't mean to write that in there. But let's go on to this one. So we're going to divide our functions. Our f function is the square root of x, and our g function is the square root of 5 minus x. Now, since we're talking about a new equation, we do got to figure out that domain. Let's take a look at the two previous domains to figure that out. This domain, x would have to be greater than or equal to 0. Now over here, 5 minus x would be greater than or equal to 0 if we subtract 5 over, but then divide by a negative 1, we got to flip that sign. We're getting our two restrictions. So we have a domain value, x is bigger than 0, but x is less than 5. So we kind of have this compound inequality coming into play. X is in between 0 and 5, but since we're dealing with a fraction, we got to be careful because notice how this square root is in the denominator, meaning that it cannot equal 0. So in this piece, since this domain was coming from our denominator, we have to lose that equal part underneath our inequality because we cannot equal 0 in this case, meaning we cannot equal 5 once we go through and solve it. So we're bringing our two previous domains into play, but you got to be careful with a fraction because we might be gaining a restriction. Notice how we cannot equal 5 in that case. Alright, so let's take a second and talk about how we can perform operations on functions in a graphical sense when we look at a picture. So in our first one, we want to take our f value and add it to our g value whenever our x value is 2. So if we find f of 2 first, okay, f is our red graph here, f of 2 would be 0, because if I put in 2, I get out a y answer of 0. So f of 2 is 0, but I want to add that to my answer for g of 2. So if we take a look at our g equation, when we put in 2, we get an answer out of -1 somewhere right there. So if I take 0 plus -1, my overall answer on this operation of functions would be a -1. Now let's try a subtraction. Let's find f of -1. So if I put in -1 in my f equation, it looks like I get 3. And I want to subtract that from my answer when I put -1 into my g equation. So -1 in my g would give me a -2. 3 minus -2 changes to a plus, so we would have 5. Alright, so let's talk about a composition. This is a multiply. Never mind, down here we have composition. So let's find g of 0, which would essentially be 0 right there at the origin. And I want to multiply that by f of 0, which would be 4. But 0 times 4 is just 0. Alright, let's do some division. If we find f of -2, that would be 0. And divide that by g of -2, which is -4. But 0 divided by -4 is just 0 as well. Alright, so now we're getting into the composition ones. Okay, these are the tricky ones because we got to find g of 3 first and then plug that into the f equation. So g of 3 looks like -1. Okay, so if this equals come on pen, if this equals -1, we want to put -1 into our f equation. So what's f, the red graph of -1, would be 3. So when we compose those functions, now our overall answer is 3. Alright, so now what we want to do is take our overall graphs of f and add it to our overall graph of g. So if we were to try to make a table of values for this case, looks like we're dealing with a domain of -2 to 3. So let's make those our x values. Alright, so when x is -2, I want to take my answer from f and add it to my answer of g. So right here of -2, if I take 0 plus -4, that looks like my overall answer is -4. Now at -1, I want to take 3 and add it to my answer of -2, which would just be 1. At 0, I want to take 4 plus 0, which is just 4. At 1, I want to take 3 plus -1, which would be 2. At 2, I want to take 0 plus -1, which is -1. And then when x is 3, I'm going to take -1 plus -5, which gives me a -6. So now that we have our overall table of values for these inputs and our outputs, let's graph these points to see what our new graph would look like. What would the graph of f plus g look like in terms of these two original ones? So if we plot -2, -4, looks like they share that point. -1, 1, 0, 4, 1, 2, 2, -1, and then 3, -6, somewhere down there. We can connect our dots. So this black graph, we would say, is f plus g. So if we were to take our red graph and add it to our blue graph, we would get this overall black graph right there. Alright, so good luck on the practice, good luck on the application, most of all good luck on that mastery check, and I'll see you guys later. Have fun composing and operating on these functions.